then we do something which is called able test. Able test. Is what if you have a series AN. So if I have a series AN from 0 to infinity, and this capital AN represents the partial sums. Right? Well, and again, with this notation, following conditions hold that this sequence of partial sums and then is bounded second is that so what actually we are interested in that when such kind of series is going to converge, when such kind of series is going to that's it. Now, such kind of series is going to converge if these ANs and DN, the series formed by ANs and DNs has these properties. In other words, from these two, one of the series is has bounded partial sums. Okay. And the second is that the other one, then typically doesn't matter. Like you can have bounded partial sums for Bn and the other property for n doesn't matter. Just one of this. This is true without loss of causality. Anyway, so I have such kind of series of convergence. So one of the series representative are AN and BN. Say AN has bounded basically partial sums. The second thing is that the other series is decreasing other sequence. Is decreasing, and the third property is that it also converges to zero. So if these three conditions are true, then you have to say that your series A and B and that's what essentially you have. For convergence of this kind of series, okay, for one series, like you have two representatives A and B and for one of the series represented by one of ANs and BNs must have bounded partial sums. Another should be decreasing and it should converge to zero. These conditions are old. And I gave this example as well. For example, imagine I have this series minus 1 over n. Now, interestingly, if we just have 1 over n, or minus 1 over n is divergent. It's a harmonic series, we have done it. But if you have this alternating series, okay, the signs are being alternated, then it is convergent. Why? So you need to choose cleverly your ANs and BNs. So what should be the series?
Bounded minus 1 or
I can choose Bn to be. Alright. Now clearly Bn has this problem. So the denominator will increase the these and this property. While with this, the partial sums, the n, are going to be either 0 or minus 1. Imagine if n is 1, then a1 is what? Capital A1. It's minus 1. If it is 2, then it should be 1 minus 1, 0. So if it is 3, again minus 1, so on and so on. So it's like an
one over to k equals to 0 to 1 then 1 to 0. Not to
okay. 1 0 doesn't matter. If you're starting from 0 here, then it's going to be 1 0 1 0 1 1. The range of this sequence is going to be 1 0 and hence bounded out. It has that property. Second property is similarly valid. Those properties are kind of valid that if it tells you that this series must be strangely convergent. Okay.
Sir, what happens if 2 is not satisfied? If only 1 and 3 properties is first and the third property is
Then the convergence of this is not guaranteed. So the series may converge
then why it is out there?
because these three are sufficient conditions for necessary. So if these three conditions are satisfied, for sure no series is going to converge. But if one of the condition is being relaxed, we don't know that we was going to happen. So we did this table test. So based on this table test, now I like to prove something very famous. I have heard that. That's called alternating series test. Have you heard of alternating series test? Any? You haven't heard it. Some have heard it, some haven't heard it. Alternating series. So in other words, if you haven't given an alternating series, how can you know what you mean by alternating series? It's like a kind of a series in which terms are being alternatively added, subtracted, added, subtracted, added, subtracted. Okay. So how you can know that a given alternating series is a convergent series? So you have this. The criteria, and the criteria are the proof of criteria, it really follows from. That's what. Okay, so here's the theorem. We have alternating series test. Suppose those following conditions are true. The first is that I am interested in okay. I am interested in convergence of an alternating series. So here is it. So the first condition that it should have is that, like imagine I have a series like Cn, which is alternated. First property that it should have is that absolute of Cn is equal to absolute of C2. And so on. So it should be absolutely decreasing actually. It's not decreasing in general, but absolutely decreasing. And the second property that it should have, that if C2m minus 1 is non-negative, then C2m should be non-positive. So in other words, we are saying that it is really an alternating series. That if one term is non-negative, the other is non-positive. And the third thing that it should have, that it will be the limit and which is to infinity of Cn. What to say? If these three conditions are satisfied, and run. So let's try to make sense of it. So I have a such kind of a series, and I'm interested in its convergence properties in this series. That one. I mean, this is going to converge potentially what properties should it have? So first line it should absolutely decrease. Okay. And if odd terms are non-negative, the mean terms should be positive, or other way around, doesn't matter. And the limit and approach is of the representative of the sequence and sum of sequence. If all these are true, then here is convergence. Now help me out that how can I reduce it so there is no need to do anything. I can just choose my A's and B's cleverly from here. I'm 100% sure that this is true. So what should I choose?
Sir, a question. Sir, won't we prove every test?
We did it last time.
Proved it?
Yes, we did it. Or based on summation by parts.
Sir, सिर्फ थर्ड से हमारा convergence to नहीं होगी सर, सिर्फ थर्ड properties हैं.
Just third set. No. That's it. That's an illusion. That's an illusion. So if the series is convergent, then it should necessarily have this property. But if this is true, it's not necessary that it should. For example, you have this famous example, 1 over n. So it's like 1 over n goes to 0, but the series diverges out. What should I choose? It should be my clever choice.
2 minus 1.
So hint is this, that if Cn has such kind of property, then Cn should look like this actually, minus 1 raised to n and close. So it should look like this. Where n runs from 0 to 1. Because otherwise you can't have it. Tell me another way by which you can have. If this is true, what should I choose?
We know minus 1 power n is bounded. So you can choose n to be this.
I'm saying that CL is going to look like this. It's not good. Maybe it's not exactly like this because you know about A and then
N should be. Chosen it to be.
okay.
Do that.
Fine. So do this. Try this. Choose in this series, choose A n to be either minus 1 power n or minus 1 power n plus 1. I start from n equal to 1.
Yes.
Okay. N plus 1. And choose B as B absolute of C. So by this choice, that you can have everyone. Lie every decimal choice, this choice happens.
Question
I mean,
fast.
so this has partial sums bounded, and
One is
for the n, these two properties are true.
Yes.
Okay. One thing that we need to verify is that here you have been given that limit Cn is 0.
Yeah.
But can we follow, is it possible to follow that if the limit n approaches to Cn is 0, then limit n approaches to
Absolute of CN.
absolute of Cn is 0. We have done it actually.
We have done it.
You can just apply reverse triangle inequality. The calculation is very such that it should. You would not even use reverse triangle inequality because the sequence is a null sequence. It converges to 0. So it follows directly. So if the conditions are satisfied, so you have to work. So when you are going to apply this criteria, so you're going to apply this criteria to those series when the series is alternating active, it's like changing the signs. Which is changing the signs. Then one potential test be like this. Should have obviously these ones. But it really doesn't mean that on alternating series is you can't apply other tests. You can apply other tests as well. I mean, if this is not working, imagine, because that's a huge demand. That's a huge demand. That's not a small demand. Not every sequence is going to have this. Okay? If one of them is missing, you can try something else. So, obviously, we can't escape from this cycle. So, like this should be there. Because if this is not true, your series is going to diverge. So this should be true. But you can have series for which maybe this is not true. But still you can apply some other test to know whether the series anyway, that's a sufficient condition for the convergence of alternatives. Okay, so let's move ahead. So, and we so we proved for sequences that if a sequence is convergent, then it's going to must converge absolutely. In other words, if Cn converges to something, then the absolute of Cn is going to converge to absolute of the limit. But you can ask a similar question for series actually. It's also true that if a series is converging, then it should converge absolutely. In other words, I say that if this is convergent, then is it necessary that this should also converge?
Yes.
Or can we go other way around? In other words, if we can know this, does it going to have any impact on the convergence of the series? That's what the next thing that we're going to do. Okay? So, absolute convergence of
Series.
okay. The fifth definition. We're going to say that the series AN converges absolutely if this series is convergent. Like taking the absolute and this series. Series formed by the absolute of A and S. So here's a little bill which shows that basically saying that absolute convergence
So this is true by comparison test.
Huh?
This is true by comparison test. This absolute convergence implies convergence. If we look the
No, that's what I want to look at. So we are saying that is convergent absolutely. This should converge. Given that this guy is convergent. This is convergent. How can you have convergence of CPL? So for the convergence, we have to apply
Compare.
apply
simply we can say
okay, but as I said, one of the suggestion is comparison test. Okay. So since absolute of an is bigger than or equal to an
for all n.
for all n, and the bigger series, okay, sequence represented by the bigger series is convergent. Then by comparison test. It's a simple application. You can also do it through Cauchy criteria. You can do it in bracket. You have to be always careful when you are applying the theorem. Then are you in the assumptions? Are you in the business? If you are in the business, apply that test. Otherwise, don't cheat. You can't apply every test, all kind of field. There are restrictions on this. Be careful. Converse is not true. Why converse is not true? So here you can see very interestingly that in sequences convergence implies absolute convergence in sequence. But there's an open question. Can we go out backward? Just think of it. I don't know. Still think for yourself, but can we go backward? Maybe we can do that backward. But here absolute convergence implies convergence, but converse is not. If you have a convergent series, it should be. Give me an example. What should be the easiest? Exactly. You can have this easiest example minus 1 raised to n over n actually. That's your CM. So what would be the corresponding? So this is convergent. But what would be the corresponding series of absolutes?
1 about it.
That's it. Okay? The last thing without wasting time, I would like to put it basically doing the algebra of C. Yes. This is something that you have to do for yourself. If I'm saying that do it for yourself, take it seriously. Okay? Here's a simple algebra series as expected. So if I have a series which can run this to A and I have another series which can run this to B, then the sum of the series is going to converge to B, and if you multiply a scalar by a series, that is scalar times. Okay. So it has kind of a linearity. That's what you have to do yourself. In this and this, and try to reduce the convergence of this. So try to take the partial sums of this series, make a Cauchy sequence, and try to reduce that basically. And using these two convergences, those partial sums are partial.
So can't we apply the limit properties of sequences here? Because summation of an is equal to limit n tends to infinity of Sn, right? If Sn is, let's say, an, then we can have Sn and Tn, let's say. They would be sequences, so...
That was a notation actually. That was a notation.
But we can take this we can take this sequence, this series, to be sequence of partial sums.
Yes. You can do that. So it's like if you have a result with you, if you have a definition, you can also rely. Okay? Now product is mentioned here. Product is mentioned. Imagine I have this kind of scene. So I have this one. And this one. Line. Again, very careful, ask mathematics. For engineers, they can say, okay, take multiply with everything and take dual and multiply with everything. It's very simplistic. Have to strongly ask the question. This is a symbol actually. That's not something that exists. That's just a symbol. We have a meaning behind it. And we have a meaning behind it. Meaning of the information. Okay. If these things are meaning, then you're going to say that, okay, what would be the meaning of taking their product? Okay. So if you take the product of two series, you should have series as a result. The question is, what should be that series? Then it should be well defined also. So we're going to say that when you have this, then you are going to have a series. Right. Cn. I need to define the meaning of Cn. So I will define Cn's through partial sums. What is Cn? So Cn is basically a sum